Good morning, good afternoon, and good evening to everyone joining us from different parts of the world. A very warm welcome to the day one of the fifth International Conference on Universal Threats in Expert Applications and Solutions, as we fondly call it UNI-TEAS 2026. I am Sneha Rathore, and it's an absolute pleasure to moderate today's online session. This prestigious conference is being organized by Shree Universe College, Apex University, and Panipat Institute of Engineering and Technology, managed by KK Consultancy Services India, and supported by University of Rajasthan, ACM Jaipur Chapter, All India Council for Technical Education, and Computer Society of India Jaipur Chapter. This year, we received an overwhelming response with over 300 paper submissions from across the globe. After filtering out AI generated and plagiarized content and a rigorous peer review process by our expert panel, only the top 80 papers were selected for presentation. Based on their performance and recommendations of our session chairs, these selected papers will be published by Springer Nature. The first half of the day one for 16 February, uh, we had an incredible series of keynotes, paper presentations, award ceremony, and discussions that truly embodied the spirit of innovation and inclusivity offline in Jaipur. As we step into the latter half of the day, we carry forward that same enthusiasm, ready to dive deeper into the thought provoking sessions and interactive presentations that will continue to shape the future of intelligent systems and digital security. With that, I am pleased to introduce our session chair for this segment. First, it is my honor to welcome Dr. Chirag Joshi, Associate Professor from Jaipur, whose insights and expertise will certainly enrich today's discussion. Thank you, sir, for joining us.
Thank you very much.
Uh, Next, it is my honor to introduce Professor Paresh Vallabhbhai Virparia from Sardar Patel University, Gujarat. Professor Virparia is widely respected for his academic contributions. Thank you, sir. Before we proceed further, I would like to share a few important instructions for all the paper presenters to ensure a smooth and timely session. Each presenter has 10 minutes to present. Please stay within that time limit. Briefly, cover your research context, objectives, methodology, key findings, and conclusion. A short question answer may follow your talk of 1 to 2 minutes. Keep responses brief and focused. And keep your mic muted when not speaking. Stay for the full session to support the fellow presenters. Also, I would like to and delighted to welcome Professor Manju Kaushik from Amity University, Jaipur. With the kind permission of our session chair, we shall now proceed with the paper presentations. I would like to invite our first paper presenter for the day, presenting the paper titled A Unified Pipeline from Filter-Based Feature Extraction to Mask Generation under the code 309. I request Mrs. Khushbu Garg, Nriped Narayan.
Yes, good afternoon, ma'am.
And Gaurav Agarwal to kindly take the virtual stage and begin the presentation. Over to you.
Yes, thank you. Yeah. Yes, good afternoon to everyone. Myself, Khushbu Garg. Today I am present a paper in a UNI-TEAS conference 2026. My paper title is A Unified Pipeline from Filter-Based Feature Extraction to Mask Generation. Presentation outlines is introduction, literature survey, scope of the study, methodology, result and analysis, conclusion, and references. Introduction. Computer vision and the deep learning, it's now possible to not just recognize the presence of object but also pinpoint their exact location within the image. Timely detection of harmful objects such as weapons, explosives, and the hazardous material is crucial for preventing incidents and the minimizing the potential damage or the loss of life. The successful implementation of automated harmful object detection system can significantly reduce the likelihood of security breaches, ensuring the safer environment for the public and the private sector. Basically, with the help of this paper, actually we find the hazardous weapons with the help of cameras. Like in this image, we have a different kind of the devices like a smartphone, remote PC, and the television monitors, and there is some another space that is camera. With the help of cameras, we can collect all the types of the things in going in the environment, and we record this thing in the CCTV DVR. Detecting harmful object through the CCTV footage has become increasingly vital and for enhancing public safety security. Basically, it is work on the institute and the airports and the bus stands and the like where the human activities are going on the regular basis or on the crowded areas. Recent advancement in deep learning, particularly with middle, like the YOLO is a you only look once, and CNN, convolutional neural network, have significantly improved the accuracy and the efficiency of these detection system. The integration of artificial intelligence, computer vision, and the machine learning offers a new opportunities to automatically detect the harmful objects such as weapons or the explosive in real time. This research aims to design and develop an intelligent harmful object detection system that improves the detection accuracy, handles the challenges like the poor lighting. Sometimes the camera is working, but because of the poor lighting and the some object is not visible clearly, and the or all image is not looking at the good, and it means the enhance the overall effectiveness of the security cameras and the surveillances. This study aims to develop an intelligent surveillance system that can accurately detect the harmful object using the advanced image recognition techniques, improving response times and the threat detection capabilities. Basically, it's a model in which it's a flow chart in which we analyze how to we detect person that person is having harmful weapons with him. First, we check the capture image. First, we capture the image. Then we check the face detect. If stress, first parameter we take the stress. Take the stress. Detect stress using CNN and the ResNet 15, and then we analyze the stress. Basically, CNN or ResNet is used to calculate the stress on the human body. And if the stress level is greater than 70, then we take the deep body scanning of a particular person. It means the person is having some hazardous weapons or some knife or some gun or some or etc. If stress level is less than 17, then we go to the light scan of the body and then detect the weapon with the help of YOLO V8. YOLO V8 is a detecting, it's a software, it's a framework which with the help of this we can detect the weapons. And if we get the weapon, then we send the alarm to the particular person. It's a literature survey where we find all the things. First is a Smith in 2020 and facial emotions, and limitation is the no real time image. And second is paper 2021. It's a technique we use the weapon detection with the help of YOLO V5. And the data set we use the open weapon DB and struggle with the heavy concealment. And third is the Jang at L 2022. In this, we limitation of this paper is the no stress correlation. And next is the Gupta's, and it's a 2023 paper, and the technique is used in this paper is the multimodal AI security. And strength of this paper is the facial and the body cues, and the limitation is lack and the ethical framework. And these are the or some literature survey that help me to final design of the paper. And we get the accuracy with the help of YOLO V3 is 97.3 in the precision. And it's in this we use the CNN and RCCNN or in SSD. Real-time monitoring and the threat analysis. This is some old paper, but in this paper we use how to check the accuracy in the real time and the large monitoring of data. an AI-based signal intelligence for the real-time threat detection. It's a paper. In this, we use the transformation and the CNN and the LSTM development and the optimization of deep learning model. It's a paper. In this we use the detection of the objects and weapon detection. And limitation of this paper is reduce the number of false positive, because sometimes we think only knife and the guns are the real object, but it's maybe a toy gun and a toy knife. It's also a limitation of this paper, because sometimes they work like a real, but it's a false positive uh, things. And next is a next is a next is a detection armed detection using the artificial intelligence and deep learning for the security. Both algorithm achieve good accuracy in the weapon detection, and method you use in a YOLO and faster RCN and SSG. The scope of this study is, the main aim of this study is to enhance the real-time monitoring capabilities and improve the security measures across the various environments such as public space, educational institute, transportation hub, and the private premises. Implementing a two-step detection approach that first identifies reasons within a video frames where the harmful objects are likely present, followed by the object classification and the continuous tracking throughout the video stream. Minimizing fault detection rate by improving, means fault detection rate means sometimes it's a toy knife, toy gun, and the etc. Main reason of this study is the minimizing the fault detection rates by improving the system ability to differentiate the between harmful object and the non-threatening items. Oh, no, guys. This study aims to create a real-time monitoring solution that accurately detect and classify the weapons such as firearms and the knives in the video fetched from surveillance camera. The study also addressed the challenges of operating in the diverse and the challenging environment conditions such as the low light setting, rain, fog, and the crowded scenes by the incorporating context-aware the AI robust and the detecting algorithm that maintain the high accuracy and reliability in the non-ideal scenarios. Main methodology we are using basically we use the three filters here. First is the clay, and second is the Gabor, and third is the Sobel. Basically, clay is used to abstract the filters, and Gabor we use the texture that enhancing the image quality, and Sobel we are using the sharpening the image. And we are using a different kind of the methodology and the different types of the steps: general system architecture, feature based pre-processing, generating mask and mask application, and the visual overlay, and output generation and file management. This is the general system architecture. First be the optional enhancement, feature based pre-processing. First we check all the features of the images, and second is a mask design. Then first we generate the features of the images, and then we collect the features, and then we use the mask on that particular image, and the mask application and the visual overlay, and then at the end we store the output of that particular image. Resultant analysis: the presentation approach, processing the input images through the organized pipeline that improves the segments and the superimpose regions on the interest. The output level that have been generated to each and the presented in this section. The conditional logical applied is analyze and robustness of the reproducibility of a proposed system discussed. First is the pipeline output categories and the analysis of the pre-processing workflow. Basically, Kile and the Gabor and the high pass filter. High pass filter is used to basically sharpening the image and the result of the images that we stored for the further use. And the KKarni detection, it is also for creating the boundaries of a image that hazardous images will be detected by the YOLO. And these are the some output images that is generated with the help of mask. It's basically an image that different kind of data set here, and we get apply the masking on that images, and then we get the enhancement of the image. Conclusion: the development of an AI powered weapon detecting system using TensorFlow represent a significant advancement in the enhancing public safety and the security by leveraging a dual stage detection framework. Basically, dual stage detection framework is first we check the location of the particular place. That at that place the harmful object can be used. It is a crowded area, it's a public area, or it's just some institute or some crowded place, classifying and tracks of the weapon in the real time, ensuring robust performance even in challenging environments such as low light condition or the crowded places. The integration of the context where AI further improve decision making capabilities, reducing false positives and the enhancing all the systems reliability. Future work will be focused on the expanding data sets, improve the model accuracy, optimizing for an edge computing enables a real-time and the cost-effective development, and ensuring ethical compliances. In short, the system is fair, transparent, and the socially adaptable. These are the references from where we get this paper help to design, and these all are the references. Thank you. Any question, please? Thank you.
Thank you so much, Ms. Khushbu Garg, for your insightful and well articulated presentation. We are now open to questions now, if any. Okay, so if there are no further questions from the audience or session chair, we shall now proceed to our next paper. I would like to invite our second paper presenter for the day, presenting the paper titled Machine Learning Approaches to Audiovisual Rehabilitation in Early Childhood under the code 310. I request Ms. Pandi Prabha and the team to present to kindly take the virtual stage and begin their presentation. Over to you, ma'am.
Yes, ma'am. Thank you. Let me share my screen. Is my screen is visible, ma'am?
Yes, ma'am, visible.
Yeah, okay, thank you. So I'm Professor Pandi Prabha. I'm working in Jain University, Bangalore. So today my topic is machine learning approaches to audio video rehabilitation in early childhood. So in this paper, mainly I'm focusing on accuracy of the model. So here the introduction, we know the children with hearing ability will have a communication barriers and language delay, and social interaction would be delayed due to rehabilitation. So traditional models which will not that much adaptable or gives accuracy to children to get the habit of it or train them with the perfect communication. So that I have come up with an intelligent mobile, whereas it is also can be included in a mobile version, and the multi-model rehabilitation system for early childhood. So this is my related work. Like I have gone through so many papers. So the papers whichever was present, it was methodology focused on audiovisual speech, and there are some CNN and convolutional neural network models which actually focused on assistive speech recognition. And my third paper, that is multi-model DL, that is deep learning, that is affective inference. And my fourth paper, that is audio-visual emotion detection, it is focusing on only the audio-visual emotion. So based on these relative work, the literature reviews, I have found that the earlier systems doesn't have adaptability rehabilitation systems. So that is my research gap. I have taken it as a research gap. Then I have come up with the existing systems. The existing system, whereas it is lagging of recognizing centric models, audio video models, and audio only work, and weak multimodal fusion and no reinforcement learning, so that it cannot do a backtracking and learn much more over a time of period. That is not possible. in the existing system. So the existing system also have some of the limitations. It is limited generalization and poor home environment robustness and no curriculum progression and no clinical validation linkages. So I have concluded with my problem statement. So currently this audio video, that AVS or rehabilitation system, do not integrate with audio, visual and behavioral signals together. So it is lagging in adaptive therapy mechanism, reinforcement learning personalization and enhancement based curriculum updates. So I have concluded with my problem says we need to design a scalable, adaptive, multi-model ML based rehabilitation system for early childhood. So this is my proposed system architecture. So whereas we have a sensor or we can have a mobile cameras, so both are considered as a device. So from the device we capture any kind of audio, video, visual, anything can be captured. So that will be pre-processed. After pre-process, so audio will be taken at an input as a CNN plus RNN neural network, and the visual video, that visual will be taken as CNN plus RNN by the behavior. Then it will be given to a multimodal fusion. So whereas it detects the classifications and it just checks the errors in that particular video and audio things, then it goes to the reinforcement learning. So whereas it will be backtracking and learning over the time of those data. Then it predicts the results for the clinical outcome. This is my algorithm overview, which I have written in the paper. So I have given only the steps here. So first, either we give visual or video, audio, anything as an input. First, it will extract that using MFCC. Then next, we will have a feature extractions. Then normalize the video frames and detect lips. Then encode features using CNN RNN model. Then fusion modulates using attention mechanism so that it can take decisions exactly where to put up. Then generate the transcript, impairment classification, then compute engagement and behavioral metrics, then oral tutor selects next exercises, then generate caregivers and clinical reports. This is my result overview. So by combining this proposing this new model, actually the experiment I have conducted using Python, that is TensorFlow and GPU, then Python 3x, any version can be adopted for this, and then my operating system. So I have evaluated classification performance, fusion contribution, behavioral metrics, engagement metrics, adaptivity metrics, then clinical outcome. So I have given here the comparison of my existing papers with those models and my proposed models. So in my proposed model, if you say the accuracy is, in my proposed model, if you have seen, my accuracy is 95% what I have achieved, and the system evaluation, that F1 score is 0.92. Then audio contribution to understand that audio accuracy is 60%. Then visual is 40%. Then error reduction is 18%. Then the task completion within that limited time is 82%. So as I observed, a stable attention fusion, better noise robustness, my proposed model is better than the other compared models with different author papers. And here I try to conclude that CNN RNN attention fusion improves actually via audio and visual recognition. Why? Because we have a reinforcement learning, which is enables the adaptive therapy. So the multimodal integration improves engagement, error detection, and clinical outcome. So in a future way, if you want to take it the same work further, we can try with these are the some kind of keys, that is transformer based language model and federal learning engagement and lingual clinic trials and cross-lingual data set expansion. So these are the further way where we can expand this research. So thank you. That is about my research. Yeah. Any questions?
Hello, ma'am.
Yeah.
Dr.
Yes, sir.
Chirag here.
Yes, sir.
Can you tell us more about the clinical outcomes from your research?
Yeah. So the clinical research, you mean you want to know what it is, or
Yeah, what kind of outcomes you have achieved? Can you tell us more about that?
yes. The clinical research in the sense here, if the children is in parallel with the childhood, right? Like if when we try to train them, focusing on those words, whatever the video, audio, which is we take it from outside the as a data set. The existing models are not capable enough of giving us the accurate results. So here the clinical model is nothing but where we are trying to train, like to give a input to such children in perfect way, so that they are also able to understand, and they will also be improving.
So have you used any real time data set for this? Or is it
Actually,
the
I have
data set which is
taken
available?
the no, sir.
You are saying
Not
that
a primary data set.
your
I have not
model will improve some
downloaded from
clinical
any.
outcomes, no?
Yeah, yeah. Actually, I have
So
not
for
downloaded
clinical
from
outcomes, we
anywhere.
need some real-time data set. That's my suggestion.
Okay. Sure, sir. Sure. I'll try doing that.
Thank you. Thank you.
Yes, sir. Yes, sir. Thank you.
Thank you so much, Ms. Mandi Prabha, for your insightful and well articulated presentation.
Thank you.
Any more questions? Okay, so now I would like to invite our third presenter for the day, presenting the paper titled Evaluating Quantum versus Classical Machine Learning under Classical Simulation Environments under the code 311. I request Mr. Sardar and his team to kindly take the virtual stage and begin their presentation. I request you to kindly present in 7 to 8 minutes. Over to you.
Good afternoon, everyone. My name is Shabdat, and today I will presenting our work on evaluating quantum machine learning versus classical machine learning under classical simulation. This work was done with my co-authors from Graphicera Hill University and Graphicera Deemed University. Sorry, I forgot to say. Um, So first of all, I want to tell about some machine learning. Machine learning is widely used for today for prediction, classification, and pattern recognition. Classical machine learning models like SVM and neural networks are very mature and efficient. But quantum machine learning is new research area that combine quantum computing with machine learning concept. In this our paper, we compare how classical and quantum model perform when both are executed on classical computers using simulators. So although quantum computing is promising, current quantum hardware is very limited and noisy. Because of this, most researchers use simulators. So the motivation of our work is to honestly check where the quantum machine learning gives any practical benefit today when compared to classical methods. Classical machine learning. In classical machine learning, we use algorithms like SVM, PCA, and neural networks. These models run on CPUs and GPUs and are highly optimized. They are fast, scalable, widely used in real-world application. In our experiment, we use SVM and PCA with combine of SVM. In quantum machine learning use qubit instead of field. Basically qubit tell about the capacity of data they can represent. We tested three quantum models: QSVM, QPCA, plus QSVM, and VQC. These models are implemented using quantum circuits and trained using hybrid quantum classical methods. During the literature review, there are some research gaps which we find. Even though uh, quantum machine learning is promising, there are still many challenges. Like this include hardware noise. Means like quantum machine learning, in quantum machine learning, most of the times error happen. There are limited of number of qubits which can be really useful. And most important, it is very difficult to convert our data to encode our data for ML models. Our work try our work try to highlight this practical issue using experiment comparison. For this, we use three benchmark data set: IRIS, WIN, and binary MNICT. IRIS was reduced to IRIS was reduced to binary to reduce circuit complexity. MNIST was used to test how models behave on high-dimensional data, while classical models were scaled using standard preprocessing. Quantum models require special encoding. uh, in classical we use SVM and PCA plus SVM, and in quantum we use QCVM, QPCA plus QCVM and variational quantum classifier. For implementation, we implement classical model in state-learn, and for quantum models were implemented in Qiskit machine learning, which is an software for quantum circuits. We use and for encoding we use different maps, like we use quantum features map and variational circuits. All experiments were executed on classical simulator under ideal condition. So about the result, when we use custom data set, in custom data set experiment, classical SVM achieved very high accuracy in milliseconds. As we can see here, classical SVM achieved 98.33% accuracy in 0.01 second, while the quantum model achieved lower accuracy and required hundred of seconds of training time. This showed that simulation includes heavy computational overhead of quantum models. In the second experiment, we use multi-data set benchmark, which are IRIS, WINE, and MNIST. Here, across IRIS, WINE, and MNIST dataset, classical model consistently achieved near perfect accuracy in very light time, while QSVM performed moderately well on small dataset, but dropped on highly dimensional dataset. VQC saw unstable performance and required the longest training time, which is 720 seconds. If we compare the accuracy, if we analyze the accuracy, classical models perform better because these data sets are well structured and classical algorithms are mature. While the QSVM works better on small data set because it has fewer trainable parameters. VQC performs depends heavily on optimization and circuit design, while which is difficult with limited qubits. Now we about the training time analysis. Classical training completes in milliseconds, while quantum simulation required exponential state calculation and repeated circuit execution. This creates a major performance bottleneck and makes a quantum models much smaller in practice. Under simulation, classical model is clearly out from quantum models today. However, quantum models are still in early development. Hybrid quantum classical approaches may offer practical benefits in the future as hardware improves. Our result shows that classical ML is currently superior in speed and accuracy under simulation, but quantum ML shows the theoretical promise, but it is not yet practical for real-world use. Hybrid approach and future hardware improvements may change this in future, but right now it's limited. Future work. In the future, we plan to test these models on real quantum hardware. We also aim to design more noise-resilient circuits and scalable pipelines. Standardized benchmarks and application to more complex dataset will be more important. To conclude, I want to say that quantum machine learning is still in very early stage. Our work shows that while classical methods dominate today, quantum approach offer interesting future possibility as hardware and algorithms improve. Thank you.
Thank you so much, Mr. Shabdat, for your insightful and well articulated presentation. We are now open to questions, if any. If there are no questions from the audience or the session chair, we shall now proceed to our next paper. I would like to invite our fourth presenter for the day, Quantum Classical Hybrid System Architecture for Multi-Temporal Change Detection in Satellite Remote Sensing under the code 312. I request Mrs. P. Rajeshwari and her team to kindly take the virtual stage and begin their presentation. I request you to kindly present in 7 to 8 minutes. Over to you.
Yeah, good afternoon, everyone. I hope my screen is visible. Yeah, so my presentation topic is Quantum Classical Hybrid System Architecture for Multi-Temporal Change Detection in Satellite Remote Sensing. So today's presentation outline is introduction, abstract, literature survey, proposed methodology, results, conclusion, and references. So basically in Earth observation satellites like Sentinel-2, so produces lots of terabytes of data daily. So, and even the satellite images are of higher dimensions. So whenever it is of higher dimensions, so processing it will be a very difficult with the classical machines. So, and these Earth observation satellites will help us for tracking the deforestation as well as the urban growth mapping and post-disaster assessment. So the major problem with this, to do this kind of key applications using the Earth observation satellites, so challenges with the classical deep learning techniques are cursive dimensionality, sparse or imbalanced temporal signals, and operational scalability. So because of the higher dimensions in the satellite image, it is really very difficult to make use of the available resources, hardware resources, and also it will improve the computational cost for processing these kind of applications. So here we are leveraging the basic advantage of the quantum computing here, like superposition and entanglement, where we are making these quantum computing circuits as a shallow networks in the classical circuits, so, classical deep learning models. So because of this power with the quantum computing, which will do the complex, which will identify the complex correlations among the multiple features in a satellite image. So we were in our paper, we have implemented this quantum computing potential as a shallow network in the classical deep learning models. So you know that these quantum computers are noisy because of the lower temperatures we have to maintain. So, and they are very limited in the qubits also, and also prone to the higher errors like greater than 10 power minus 3. So we have used the simulators here, IBM simulator, IBM Air simulator, Qiskit simulator we have used for implementing our task. So what we did is like we have integrated both the quantum as well as classical techniques and come up with a hybrid architecture. So as I just now informed, all these integration of these quantum circuits in the classical training process, so which had improved improved the accuracy as well as the reduced the number of parameters for processing. And here in the literature, so the classical ML techniques, some of the authors have used the shallow quantum circuits with a lower depth. So they have also achieved a very good results. So, and they use a kernel-based and variational quantum algorithms, and which are very useful for identifying the nonlinear patterns in satellite imagery. So in some other authors have used the similarity measure with the help of that. They have identified at the 2 timestamps. They have tried to find the change detection here. Then after in another paper, like the authors have addressed the multi-temporal change detection, where they have used the at different timestamps, the change detection has been done with the help of the available quantum neural networks, like they have used the variational quantum networks, and also they embedded these quantum circuits in the classical techniques like CNN, LSTM, and vision transformers. Along with that, they have used these quantum circuits and also applied the approximation techniques, optimization techniques for reducing the number of parameters. So, and then the proposed methodology in my system. So the input for my system is like multi-temporal sentinel-2 sequences, which are of multiple satellite images we are taking, where each image is of the size h by w by 13. 13 is the here spectral bands. Totally 13 spectral bands are there. So like visible ranges, visible bands like RGB, and invisible infrared bands, okay, and shortwave infrared bands, like that. There are 13 spectral bands are mentioned and are used in the model, and the size of each image size is h by w. Spatial dimensions we are using, and from this the output is binary change map. So we are calculating a change map value, which is either 0 or 1. 0 refers to is there is a change detection at a different timestamps, whereas 0 refers to no change, and 1 refers to change detection. And this is a probabilistic change value, where the probable value is of 0, 1. Again, 0 refers to no change, and 1 refers to change in the different temporal values. So the proposed model has been provided in this diagram. So first, what we are doing is we are taking the series of multiple satellite images from the Sentinel-2. Then here classical pre-processing we are applying with the help of the ML and DL techniques. So now the feature extraction part will be done in the classical pre-processing models, and the feature extraction extracted features will be given as input to the quantum feature map, quantum circuit. So this quantum circuit uses the conditional Z networks and as well as the rotation Z networks. So these circuits will be of depth 3, and these will do feature embedding as well as the optimization and kernel estimation. So now it will this quantum circuit will reduce the less number of parameters. The higher dimensional features will be reduced to the lower dimension features, and these lower dimension features, which are optimized number of parameters, will be given to the parallel STM for temporal feature extraction, and for the spatial feature extraction. So QSVM has been used, and these two will be combined. The results from these at different temporal levels will be combined, and they are in a stage called fusion stage. And now this fusion stage will be finally calculating the change detection value, and this change detection value is either 0 or 1, which reflects the output, whether at a particular timestamp T1 to Tn is there any change in the respective land usage or any other urbanization or like that. So here in the classical pre-processing, as explained in the diagram, each step has been given. So in the classical pre-processing, so first we normalize the spectral data and extract the patches to reduce the quantum burden. So here we will be applying the min-max normalization for each band, which will be normalized between the 0 to 1. And also there will be the satellite images. Sometimes there will be a cloud masking. So cloud will also be visible. So that may cause sometimes determining the objects properly, like buildings, and that may be the shadow of this cloud sometimes will be considered as an river, like that. So in order to avoid that, so cloud masking technique will be applied here. And we are extracting from the satellite image 8x8 patch with a stride 4, and then temporal alignment via phase correlation. And for each patch, a special location I, j at timestamp t will be calculated like this. So a patch is of the size 8x8 for 13 spectral bands will be considered. And in the second step, so now from the first step, the features which are extracted of the patch size 8x8 for 13 bands will be given as input to the quantum feature pre-processing. So in the quantum feature pre-processing, so totally now this 8x8 by 13 will give you the 832 dimensions. Now these are of higher dimensions. So these patches will be now reduced to 40 dimensions quantum features using the quantum circuit. Further, the steps that are followed here is classical, PCA will be applied to reduce the 832 dimensions to 32 dimensions. So with 94% variance. And the next step is encoding. This encoding will use a quantum circuit with the conditional Z circuits. So which will be calculating the encoding here for 32 dimensions. So then after entangling is applied for encoding operation of each of the patch, P bar refers to patch. So encoding of that patch will be done for 32 dimensions with an angle of rotation angle of rotation across y-axis on the block sphere and with a rotation angle of pi p power pk. Pk refers to the kth patch. So feature extraction will be done, and here in the circuit there will be 3 repetitions of ry and cz, where it will be calculating the respective feature extraction values. Then the measurement will be done for 20 qubits. So here every patch will be assigned to each qubit, and then from that here finally we are going to encode the 32 qubits here, so which will be again mapped to respective cosine or sine embeddings in order to give that quantum future embeddings into a classical data again. So for that here we are doing this measurement for every 20 qubits. We are converting that into classical data, and here the total circuit depth has been taken as a 6 layers, and then training will be done. Then in the stage 3, dual path temporal analysis is done. Then classical LSTM is applied for temporal extraction of the data at a different timestamps, and then quantum kernel SVM path. So this temporal aggregation per head K recurrent style. So we are going to trying to decode the quantum qubits into the respective classical bits here at different levels, and finally we are going to classify whether there is a change in the different temporal values or not with the help of this QSVM, and we'll be reducing that to the 2 dimensions finally. So then in the fusion and output, so now from the 2 dimensions finally we are calculating the probability value here with the help of attention mechanism. So we are parallelly taking the input temporal data from the LSTM and the spatial data from the QSVM and applying the attention mechanism here. And in the attention mechanism, it uses a softmax value, which will convert this coefficient value into normalized value between 0 to 1. Probabilistic value it will convert. Then finally, we'll be getting the probability value. So if the changed pixel value is greater than 0.5, the output value is 0.5, then there is a change detected. Otherwise, the change is not detected. So then finally, this is a loss function we have calculated from the whole classical and as well as the quantum circuit. So focal loss plus spatial regularization, the loss has been calculated here. And then for implementation of this, the 3 data sets I have used from Sentinel to satellite with a 20-meter resolution, Amazon deforestation, Sundarbans tidal changes, Ganges data urbanization. These are the 3 data sets available with these dimensions of satellite images I have taken for 36 months, 24 acquisitions from the timeline of these things. These are the chain detections have been detected after implementing. So now here in the experimental setup, so the baseline architectures I have considered for comparison are CNN LSTM, UNI-TEAS, visual transformers, and random forest. So here, because real quantum circuits are noisy prone, so in order to avoid that, here I have used the simulators here, IBM Qiskit Air simulator for implementing my work. So here classical for classical implementation, we use NVIDIA A100 PyTorch and Atom Optimizer, which is best for spatial feature extractions, and for the batches of 16 and 50 epochs we run. And then the training and validation and testing will be done like from 1 to 24 months of data we have taken as training, validation 25 to 30 months data we have taken, testing 31 to 36. And the metrics we used for measuring the change detection is precision, recall, FN score, and accuracy. Kappa is for learned usage, inference time. These are the results. So we have compared with all the other classical methods as well as the quantum methods. With the quantum shallow network with depth 3 and depth 6. So which is QMCD light and QMCD full. If the results, if you observe, so quantum integration in a traditional classical deep learning models will improve the results here in precision, recall, and FN score and accuracy and kappa value. So even here the results, you can find the key findings, the quantum advantage, which had improved from 3 to 7% of F1 score across the different data sets, and parameter efficiency, there's 68% of reduction in actual classical implementation. And inference speed up, 7.2% improvement is there. And dual path synergy had also made us to reduce the number of parameters, and robustness also less than 2% of variance. And here this is a feature extraction efficiency. So here we have used PCA to that which is used for reducing the higher dimensions to lesser dimensions. So here if you observe here, quantum feature map had come up with a less time here compared to the other. And results robustness to NISQ. So we have tested on different polarization technique, depolarization values for noise levels, 0%, 2%,
Sorry for
5%.
interrupting, ma'am. I
Yeah.
request you to kindly wrap up in 2 minutes.
Yes. This is a conclusion. So the conclusion is like integrating. Whenever we need to process the higher dimensional data like satellite images, it is very difficult to process with the available hardware resources today with the classical machines. So integration of these quantum networks in the classical machines, which will create a hybrid machines, will definitely improve the resources can be utilized, and even finding the correlations, and even improves the accuracy levels, so which will be especially useful in earth observations. That's it. These are the references which are used. Thank you so much.
Thank you so much, Ms. P. Rajeshwari ma'am, for your very informative and well-structured presentation. We are now open to questions, if any. Okay, so if there are no questions from the audience or the session chair, we shall now proceed to our next paper. Now I would like to invite our fifth or the last presenter for the day, a comparative analysis of multi-factor approach for suicide ideation detection from social media text under the code 325. I request Ms. Jayashree Suresh Sonawane to kindly take the virtual stage and begin their presentation. I request you to kindly present in 7 to 8 minutes. Over to you, ma'am. Excuse me, ma'am, you're not audible. Ma'am, you can start the presentation now. Ma'am, you can share this entire screen and you can continue. If there's any issue, you can email this to me or you can share this to my number. I will share the screen then. You can note my number. I will tell you. Ma'am, you're not audible. You have to unmute yourself. You're not audible, ma'am. Ma'am, you're not audible.
Sneha, is ma'am presenting the paper?
No, she has left the meeting.
Okay. So is there any other presenters left?
No.
Okay, then we can wait for 5 minutes, then we can end the meeting, okay?
Okay, sure.
Sneha, I think we can end the meeting.
Sure. With that, we conclude today's paper presentation session at UNI-TEAS. We sincerely thank all our presenters for their valuable contributions and our audience for their active participation. A special thanks to our session chair for guiding the discussion with clarity and depth. I would now request all participants.
Hello, ma'am.
Hello.
Ma'am, I'm audible now.
Yes, I'm audible now.
Jai Shri Sonali.
Okay, so you can present now.
Okay. Good afternoon to all respected panel members. I am myself Joshi Sonone. I am here to present the topic comparative analysis of multi-factor approach for suicide ideation detection from social media text. My paper ID is 325. Introduction. So, suicide ideation refers to the thoughts related to the self-harm or suicide. So it is increasing especially among the young people, or I can say it is among the adolescent people. It is in between your childhood and the youngest people. So for early identification can help prevent the suicide, but traditional detection methods are often insufficient. So for that, the next slide is for the motivation. So most individuals expressing suicidal thoughts do not consult the professional. However, they frequently share their emotions on social media platforms, making this platform valuable for earlier detection using the automated systems. So there are the earlier various approaches are there for the suicide ideation that mainly focus on the linguistic indicators. Psychological factors are also evolved over the time, and the protective factors are ignored over there. So here, the proposed multi-factor approach is there, which is going to extract the risk and protective psychological factors. So here, in my presentation, there are the segment posts are also considered, which are based on the stress level, and model temporal evolution using the long short-term memory LSTM is used.
So proposed multi-factor approach is consists of so here the research methodology diagram is there. So there is a data set is given taken from the radiate data set, and then it is given for the feature extraction. Features are extracted with the help of the risk features and the protective features. And then it is given to the temporal and spatial concentration, and then it is given to the LSTM classifier to classify into the two categories, the suicide ideation and no suicide ideation. So here it is, we can say it is different from the whatever the traditional method that we have studied. So here the psychological factors are also considered. So when we consider about the risk factor, it is going to have the hopelessness, impulsivity, abuse, conflicts, they are considered. In the protective factor, reasons for living, resilience, threats that are considered, and factors are distributed across the post. So here the neutralization mechanism is also used. So for the neutralization mechanism, two separate LSTM for the risk and protective trajectories are considered, and mutual modulation of factors are over time, and that improves the discriminative ability. So here the existing model is compared. So into the existing model, here it is the proposed multi-factor factor. Into that the risk and protective trajectories with the neutralization are considered. But when it is compared with the other model, that is the bidirectional LSTM CNN, ALPTCN, then LSTM attention CNN. So here they are just using the bi-LSTM plus attention and the convolution neural network. They just consider the TCN self attention and the LSTM. And this LSTM attention CNN, it considers the encoder and decoder with the attention. The features are used. The overall proposed multi-factor approach is basically mainly focuses on the features they have used, which are categorized into the risk and protective psychological factors. While LSTM CNN is going to have the word embeddings, LPTCN going to have the word plus temporal features, LSTM attention CNN is going to have the word plus context factor. Temporal modeling, there are the two separate LSTM are there. One is for the risk factor and another one is for the protective factor. Here just bi-LSTM is used, here the bi-TCN plus the LSTM is used, and here the encoder RNN is used. Psychological factor are explicitly included in the proposed multi-factor. The psychological factors are not included into the rest of the models. Emotion stress handling are explicitly the temporal modeling. So we are just not comparing the one post. We are taking a series of posts to compare that. So key strength is holistic and interpretable SI modeling is developed over here. Here it is based on only on the strong textual baseline. It is good long range pattern and it is for the context of its sequences. So dataset which I have used, that is the Twitter dataset 1, which is the moderately balanced data is there into that dataset. In Twitter dataset 2, there is imbalanced real world data is taken, and for the Reddit dataset, there is a large balanced dataset given. So likewise, this multiple dataset with the multiple different size are and they are distributed across the different classes, and there will be used to evaluate the robustness as well as the generalization capability of the proposed approach. So the performance matrix is calculated with the help of the accuracy, precision, recall, their F1 score, all they are calculated. And ROC, OC curve is also taken over there. So for that, to show that, we are taking the we have become the different 4 classes. The variant we have taken, C1 is going to have only the textual embedding. C2 is going to consider only the risk factor, C3 is going to consider only the protective factor, and C4 is going to have the proposed solution combining both risk as well as the protective factor. So we compare that. So we can see that whatever our approach factor is there, which is getting the highest accuracy of the 96.1, the precision of that is 96.3, recall is almost the 94, and F1 score I got is the 95.8. When I applied the second data set, that is the Twitter data set 2, and I have compared the accuracy, precision, recall, and F1 square. So for my proposed model, I'm almost getting the 95% accuracy for that. Precision is almost the 95.9, recall is 92%, and F1 score is 95%. When I compare this, I have applied then the Reddit data set on my proposed approach. So I am getting the accuracy of the 96%, precision is of the 96.5%, recall is of the 95.4%, and F1 score is of the 95.8%. So I also applied the ROC AUC analysis also for across the all the data set, and from that I got that the conclusion as a I get the better class separation over there, and whatever the false positive is rate is there, whatever reduced false, it is going to reduce the false alarms. So I'm going to conclude here. So linguistic only SI model are less accurate than that of the multi-factor approaches. Whatever the seed for proposed model is there, that variant which has the highest accuracy, and it is going to lower the false positive rate. Temporal neutralization of both risk as well as the protective factor improves the prediction, and proposed model generalize the well on balance as well as the imbalanced data set across the platform. As we have seen the different data set like the Twitter data set 1, Twitter data set 2, and the Reddit data set. Thank you so much for my presentation, and these are the references. Any questions? Hello.
Thank you so much, Mrs. Jayshree Suresh Sonawane ma'am, for your informative and well-articulated presentation. We are open to questions now, if any.
Okay.
Okay, so there are no questions. With that, we conclude today's paper presentation session at UNI-TEAS. We sincerely thank all of our presenters for their valuable contributions and our audience for their active participation. A special thanks to our session chair for guiding the discussions with clarity and depth. I would now request all participants present to kindly switch on their cameras as we take a virtual photograph to capture this memorable session.
I request Karishma ma'am to kindly off her screen. Ma'am, can you please stop sharing the screen so that we can take a photograph together? Thank you so much, ma'am.
Done. Thank you all, and we look forward to seeing you in the next session. Have a great day ahead. Thank you.
Thank you so much, everyone. Thank you, Sneha, for moderating the session. Thanks a lot.
Thank you, ma'am.
Thank you, ma'am.
Okay, thank you, sir.